Hey, we're students from Arizona State University Structure and Defects Lab, and we're here to demonstrate for you how to spin coat a polymer thin film sample and then characterize it using a confocal microscope.
In the spin coater, the substrate is rotated at high speeds, which causes the deposited solution to spread across the substrate by centrifugal force, creating a thin, uniform film on the substrate. This can be seen in the diagram on the slide. The thickness of the resulting film can range from a few nanometers to a few microns. The thickness of the film depends on the speed of the spin coater as well as the viscosity and concentration of the solution and the solvent. Since spin coating can create films on a nanometer scale, it has become widely used in the semiconductor industry for processing wafers. Spin coating is also used in cleaning applications, photolithography, and developing films on microscope slides. The advantages of spin coating are the simplicity and relative ease with which the process can be set up. Spin coating can achieve thin and uniform coatings, which is another advantage. The high spin speeds result in high airflow, which leads to faster drying times, which results in high consistency at both macroscopic and nano-length scales. One disadvantage of spin coating is that the actual material usage in a spin coating process is typically pretty low. Only around 10% of the material actually turns into the film, with the rest being flung off the side and wasted.
Hi, I'm going to show you how to prepare our thin film samples by spin coating. Before spin coating, the solutions first have to be synthesized. For our experiment, we dissolved crushed polystyrene beads into our solvent, toluene. We made varying concentrations from 50 to 140 milligrams per milliliter. The reason we made these varying concentrations was to study the effect of concentration on final film thickness. After making our solutions, we used a vortex mixer to increase the homogeneity and increase the rate of dissolution. Now that we've synthesized our solutions, it's time to spin those solutions onto our substrate. For this experiment, we used a 1 millimeter thick quartz substrate. We also used this instrument, an oscillus spin coater, which has parameters which can be set, such as spin rate and spin time. For this experiment, we used a spin rate of 1,500 rotations per minute and a spin time of 40 seconds, which does not include the time it takes to ramp up to our maximum speed and to deposit our solution. To deposit our solution, we use a non-traditional micropipetting technique to deposit 125 microliters of our solution. Let me demonstrate this technique. First, we pre-wet the pipette into our solution. Then, I'm going to insert the pipette a few millimeters below the surface of the solution and push down to a full stop. Now let's start our run. I'm going to wait 10 seconds for the speed to ramp up to the maximum speed of 1,500 rotations per minute. Then I have 5 seconds to deposit our solution, taking care to only push the pipette down to the first stop. This is done to ensure that no air bubbles get onto our substrate and mess with the uniformity of our film. Now I wait 40 seconds for our solution to continue spinning onto our substrate. After these 40 seconds are up, we will carefully take our sample and put it under vacuum in a desiccator overnight to minimize our impurities in the film.
There are several relevant parameters that affect the final thickness and uniformity of the thin film deposited through spin coating. The first, and the one most closely linked with the final thickness, is the rotational speed of the instrument during the spinning phase. The final thickness of the deposited film is inversely proportional to the square of the spin speed, so faster speeds result in thinner films. The second relevant parameter is spin time. For the first few seconds, the film thickness decreases rapidly as the solvent is forced off of the substrate due to the centrifugal force. However, the film thickness will plateau after a certain time and will not decrease substantially any further unless the rotational speed is increased. The exhaust volume, or the rate at which the air containing the solvent molecules is pulled away from the substrate, is another factor influencing film thickness and uniformity. A fast exhaust will increase the drying rate and thus the thickness of the film, but can negatively impact uniformity. Concentration of the material in the solvent being spin coated also intuitively is proportional to the final film thickness. Finally, the viscosity of the liquid being spin-coated will influence the final film thickness. A more viscous liquid is more resistant to the centrifugal force and thus will result in a thicker film, proportional to the viscosity of the liquid. An engineer can develop a process using these parameters to deposit a film of a desired thickness.
Next, we'll be discussing the confocal microscopy. The confocal microscope combines the high-resolution imaging with a depth measurement to give the user a view of the sample's depth through a 2D image. Some of the features of the confocal laser scanning microscope, or CLSM, include obtaining very accurate height information about a sample, performing optical sectioning to provide a reconstruction of the sample into a 3D image, and Z-control, which allows the microscope to focus on the focal plane and for precise movement along the sample. Like any optical microscope, the image resolution is limited by the microscope's lens size and the wavelength of the light gathered. Some of the many different modes in confocal microscopy include C-laser differential interference contrast, or DIC, laser and optical, and high dynamic range imaging, or HDR. The DIC mode separates and recombines light to produce an image with a 3D appearance. The laser and optical mode creates a combined image of varying focal planes, giving an all-in-focus image of a 3D object. The HDR imaging mode optimizes the image to include the bright and dark areas of the image, displaying the sample image without distorting its contrast. Here we have images of the tail side of a penny. The image displayed here is for the C-laser DIC mode, which displays a composite of all the laser data. Below, you can see how the image is viewed under the other modes. With optical, the image is projected as viewed by the naked eye. The laser intensity mode displays the intensity of the laser as it reflects at each point, providing a higher quality grayscale image of the sample. The height mode gives a color map of the sample that helps distinguish the image's depth, which can also be displayed in 3D.
This is the Keyence VKX150 laser confocal microscope, and today we'll be using it to determine the surface roughness of our polystyrene spin-coated thin film. First, we'll want to turn the instrument on by pressing this button and waiting 5 minutes for the laser to stabilize. Once the laser is stabilized, we'll want to put our sample onto the stage. This is our polystyrene thin film on a quartz substrate. Once the sample is on the film, we'll use our X and Y knobs to get the sample into view. We've used our coarse and fine knobs to get our image into focus, but another way is to use the autofocus button. Once the image is in focus, we'll go into the Measure tab and set our upper and lower positions. The upper position is where the foreground is in focus, and the lower position is where the background is in focus. After that, we'll start our measurement and save it as a VK4 file. We can then open our VK4 file in VK Analyzer and select the Surface Roughness tab. After that, we'll select all areas and select a desired area to find the surface roughness. Within the selected area, we can see that our RA value, which is the mean surface roughness, is 0.242 micrometers, and this also gives us other values such as RQ and RV.
There are a few ways to determine the roughness of a sample with confocal microscopy. The computer software can provide values for surface roughness, such as the mean roughness of surface area, the maximum depth of the valleys in a sample, and the root mean square of roughness, which is another kind of average value. A confocal microscope's resolution is defined as the minimum distance between two distinguishable points. Just like a conventional optical microscope, the resolution is limited by the lens numerical aperture and also by the wavelength of visible light, which is 400 to 700 nanometer. In short, the confocal laser scanning microscope is like a conventional optical microscope with a laser beam. CLSM works by passing a laser beam through an aperture and then focusing the beam with an objective lens onto a targeted area of the sample. The laser scans across the sample, and the in-focus areas of the sample are collected into the photomultiplier tube. Through vertical optical sectioning, the entirety of the image is eventually brought into focus and added to the resulting image.
Thanks for watching!
Subscribe.